You have heard the ultimate rule of the universe: nothing moves faster than light. It is a physics fact, taught in every school and featured in every sci-fi movie. But have you stopped to think about why? Why does this speed limit exist? It defies everything we experience every day. Think about moving a car or a spaceship. If you apply a force to it, if you push it, it speeds up. If you apply more force, it speeds up even more. Our common sense tells us that if you keep applying effort, that object should just keep gaining velocity forever. The idea that there is a fixed, unbreakable ceiling on speed feels wrong, like a fundamental cheat in the cosmic rules. The concept of limits has been around for centuries. Long ago, people wondered about escape velocity. That is the speed you need to escape the pull of a planet or a star. For Earth, that is about 8 miles every second. For our Sun, it is much faster, around 400 miles every second. Now, imagine an object that is so heavy and so compact that its gravitational pull at the surface is immense. People like John Mitchell and Laplace, working hundreds of years ago, wondered what would happen if you made a star so massive that the required escape velocity was actually greater than the speed of light. They called these hypothetical objects dark stars because light could not get away from them. But this simple concept of dark stars, while interesting, uses outdated ideas of gravity. It treats light like a thrown rock, fighting a pull. When Albert Einstein came along, he changed everything. He suggested that gravity is not a mysterious force pulling objects together, as Isaac Newton believed. Instead, Einstein stated that mass creates a curve or a dent in the fabric of space itself. Then, any object moving, whether it is a planet or even a ray of light, simply follows the shape of that curve. Matter tells space how to curve, and space tells matter how to move. If we shrink the Earth down to the size of a sugar cube, we get a black hole. If we crush the Sun down so it is only a mile across, it becomes a black hole. The resulting dent in space is so deep that everything falls in forever. Even light has to follow this curve. But why does light itself set the ultimate speed limit for everything else? Why is light restricted to one fixed speed? To figure this out, we must start by truly understanding what light is and how weird it is compared to everything else you touch and see. Ask yourself what light really is. The visible light we see is one of the universe's wonders, yet it only gives us a tiny, skewed view of reality. For centuries, people struggled to figure out if light was made of particles or waves. In the 1800s, Scottish physicist James Clerk Maxwell figured out that light is a wave specifically, an electromagnetic wave. He realized that electricity and magnetism travel together as waves, and when he calculated the speed of these waves using math alone, he found they moved exactly at the speed of light. This was the first major step toward understanding the fundamental nature of light. But Maxwell's finding was about waves. Later, physicists understood that light also behaves like a stream of tiny particles called photons. This dual nature light, acting as both a wave and a particle, is one of the deepest mysteries in physics. Now let's talk about the full spectrum. The visible light, we see the colors of the rainbow, from red to violet, is just a sliver of the total energy flowing through the cosmos. If you compare the reddest light we can see to the bluest light we can see, it is only a factor of 2 difference in wavelength. This range is analogous to only hearing 1 octave on a piano. If the entire range of light that travels through the universe spanned 9 grand pianos laid side by side, our eyes would only be able to hear the music from 1 central octave. The full electromagnetic spectrum spans 65 octaves in total across 9 grand pianos, meaning we miss almost all of the information raining down on us. This spectrum includes long radio waves, microwaves, which cook food, infrared light, which is heat radiation detected by William Herschel centuries ago, ultraviolet light, which causes sunburn, high-energy X-rays, and extremely powerful gamma rays. All these forms of light are fundamentally the same thing, electromagnetic waves traveling at the same speed, just possessing different wavelengths. The key to the speed limit rests with those tiny particles of light, the photons. Photons have 0 rest mass. They are pure energy bundles without the mass component that defines normal matter, like atoms, electrons, protons, or neutrons. Since photons are massless, they must travel at c. This isn't a maximum speed they are trying to reach, it is their default state, determined by their nature. If a photon were to slow down, the rules of physics predict it would gain mass, which contradicts what we observe. Therefore, light speed is not a goal for photons. It is the single constant speed they must always maintain. This simple fact about masslessness sets the speed limit for everything else in existence. The absolute speed limit of the universe is a built-in consequence of how energy and mass are related, an idea formalized by Einstein's famous equations. The reason normal objects can never reach the speed of light is due to an unbreakable relationship between mass and energy. Consider a massive object like a spacecraft moving through space. When you apply energy to push it, you increase its velocity. But according to relativity, you are also adding to its effective mass. The faster the object moves, the more massive it gets. This happens subtly at slow speeds, but as the object approaches the speed of light, its mass starts to shoot up dramatically. Imagine you are trying to push a car. Easy, right? Now imagine trying to push that same car when it weighs as much as a small skyscraper. It gets much harder. Similarly, as a spacecraft speeds towards sea, its resistance to further acceleration increases because its mass is soaring. If an object built of normal matter were to somehow reach the speed of light, its mass would become mathematically infinite. To move an object with infinite mass, you would need an infinite amount of energy. Since obtaining infinite energy is impossible, nothing with mass can ever truly reach EC. The speed of light is the universe's maximum speed for energy transfer, and mass is the penalty for being slower. This principle applies not just to spaceships, but also to the most violent events in the cosmos, especially those involving extreme gravitational warping. Remember, gravity is the curve of space. Matter dictates how space bends. If a concentration of mass is extreme, like a supermassive black hole, SMBH, in the center of a galaxy, the space around it is bent severely. Light must follow this warped path. For objects outside the event horizon of a black hole, the force of gravity is fierce. Gas falling toward this region spirals inward, forming an accretion disk. The friction and compression in this disk heat the material to millions of degrees, causing it to glow fiercely, often brighter than all the stars in the host galaxy combined. This phenomenal energy release is a function of gravitational potential energy being converted to light and heat. This conversion is extremely efficient, transforming up to 40% of the falling matter's mass into radiation. By comparison, nuclear fusion in stars converts less than 1% of mass into energy. The fact that light speed is fixed ensures this energy conversion is possible and sets the ultimate rate at which matter and energy communicate across the curved expanse of space-time. Albert Einstein's work not only set the physical rules for speed, but also showed that space and time are interconnected and flexible. This is the core of his theory of relativity. Before Einstein, most people, following Newton, thought of time and distance as absolute constants the same everywhere, all the time. Einstein showed this was wrong. If you're moving extremely fast, your experience of time and distance changes relative to someone standing still. This isn't just an illusion, it's the physical reality of relativity. When an object approaches light speed, two major things happen. First, time slows down for the moving object. If you were traveling on a spacecraft at 99% the speed of light, an hour for you might be days or weeks for people back on Earth. You would age much slower than your friends watching from a stationary position. Second, distances shrink in the direction you are moving. The universe appears compressed, an effect physicists call length contraction. These effects are two sides of the same coin, the universe adjusting itself to ensure that everyone, no matter how fast they are moving, measures the speed of light to be exactly the same constant value, c. The speed of light is the only absolute constant in the universe. Everything else, including time and distance, must be relative. To understand why this is fixed, think of light as a messenger racing across the cosmos. The speed of light, roughly 186,000 miles per second, is the fastest rate at which information can possibly travel through space-time. Since nothing can exceed c, the universe maintains order by changing the perception of time and distance for fast-moving observers to protect that constant value. This profound insight, which emerged from theories developed in the 1900s, confirmed that energy and mass are interchangeable. Matter is stored energy. When we move an object with mass, we are pouring energy into it, but because of relativity, a significant portion of that energy converts into mass as the speed increases. This is why the final barrier to c cannot be broken. Crossing it would require converting an infinite amount of energy into mass, resulting in infinite resistance. This limit is deeply woven into the geometry of space-time itself. Einstein's theory is sometimes simplified by imagining space as a giant sheet being warped by mass, which governs the paths of objects and light. But the full power of his idea is that time itself is warped and stretched, especially near massive objects like black holes. The time dilation effect near a black hole is so severe that, when viewed from the outside, time appears to stop at the boundary called the event horizon. These concepts confirm that c is not just a speed limit for light, but a fundamental speed for all cause and effect in the universe. If reaching the speed of light is impossible for anything with mass, what happens to matter that gets very, very close? In the deepest parts of the cosmos, we observe stunning phenomena that approach c. The most powerful examples are relativistic jets. These are narrow, energetic beams of ionized matter, known as plasma, shot out from objects like supermassive black holes, SMBHs, or smaller black holes and neutron stars. They are often seen stretching millions of light years across space. These jets are not formed inside the black hole, as nothing can escape the event horizon. Instead, they originate from the matter swirling around the black hole in the accretion disk. This orbiting material is highly charged, creating powerful magnetic fields that twist into a cone shape near the poles. The particles and radiation in the disk are funneled out along these fields and accelerated to speeds extremely close to light speed. This process is so energetic that it is thought that the energy is extracted directly from the rotation or spin of the black hole itself. A fascinating example is the black hole at the center of the giant galaxy M87, which shoots out a colossal jet extending thousands of light years. When astronomers captured the first real image of a black hole's accretion disk, they confirmed the source of this massive power. We also see similar, though smaller, versions of these jets coming from objects called neutron stars. For instance, one neutron star in the Milky Way has a jet moving at 80% of c. This confirms that the mechanics governing these relativistic phenomena scale across different sizes of cosmic objects. What about matter here on Earth? We regularly accelerate particles in enormous rings called particle colliders. When physicists push these particles, usually electrons or protons, close to c, they observe the predictable effects of relativity. Their mass increases, requiring greater energy input for every fraction of speed gained. The biggest challenge in accelerating anything to near light speed is the exponential relationship between speed and mass. To accelerate a gram of matter to 99.999% of c would require more energy than humanity uses in decades. This physical hurdle is why interstellar travel using traditional methods seems confined to science fiction for now. We simply cannot carry enough fuel to fight the accelerating mass increase. Even the breakthrough Starshot project, which aims to use powerful ground-based lasers to push tiny spacecraft, only aims for 20% of the speed of light. This fixed speed barrier forces us to reckon with the massive distances in space. When discussing the speed of light and black holes, several common misconceptions usually arise. Let's look at three major ones based on the laws of physics. Myth 1. We have observed objects moving faster than light. This myth usually comes from observations of relativistic jets, like those ejected from black holes. Occasionally, astronomers see jets that appear to move across the sky at speeds greater than c. This is called apparent superluminal motion. This movement is not real. It's an optical illusion caused by geometry and speed. If a jet is moving toward Earth nearly at the speed of light, the light emitted from the front of the jet has less distance to travel to reach us than the light emitted from the back. This tricks our instruments into calculating a speed faster than light because the object seems to cover the distance in an impossibly short amount of time. It is proof of extreme speed, but it never actually breaks the cosmic rule. Myth 2. Black holes are cosmic vacuum cleaners that suck everything in. This might be the most common misconception. Black holes are not vacuum cleaners. They are regions where the curve of space is extreme, but their gravity outside the event horizon is exactly the same as any object of comparable mass. If our Sun were magically replaced by a black hole of the exact same mass, the planets would continue orbiting in their current paths. The black hole would only pull you in if you got too close to the event horizon. Gas and dust that spiral into an accretion disk do so because they are in complex orbits that lead them inward, not because the black hole is sucking them. The visible evidence of this is the extreme brightness of accreting black holes. If black holes simply sucked everything in instantly, the intense light, X-rays, quasars, would never be produced. The light we observe is created by matter heating up and radiating energy before it crosses the horizon. Myth 3. Gravitational waves travel slower than light. Gravitational waves are ripples in the fabric of space and time itself, often caused by the collision of massive objects like black holes. Since they are not light, people sometimes assume they must move slower. However, evidence suggests gravitational waves travel exactly at the speed of light, c. Theoretically, gravitational waves are carried by massless particles called gravitons. Just like photons being massless mandates they must travel at c. Observations of gravitational wave signals from merging black holes match simulations perfectly, meaning they show no distortion over cosmic distances. This lack of distortion confirms that gravitational waves are not slowed down, setting a very sharp limit on the idea that they might possess any mass. This fact reinforces that c is the universal speed limit for all information transfer, whether it involves light or gravity itself. The existence of a fixed speed limit, c, coupled with the immense scale of the universe, fundamentally shapes our reality and our ability to study the cosmos. Imagine the sheer size of the space we inhabit. Our Milky Way galaxy contains hundreds of billions of stars, but these stars are separated by enormous distances. For instance, our solar system is currently traveling around the galaxy, but it takes 250 million years just to complete one orbit. The vast majority of our galaxy is made up of dark matter invisible mass holding everything together. The distances between galaxies are even larger. Our nearest large neighbour, the Andromeda Galaxy, is 2.5 million light-years away. Because of c, distance is directly translated into time. If light moved instantly, the universe would have no history, and we would see everything as it is in the present moment. The fixed speed of light turns our telescopes into time machines. When we look at the Sun, we see it as it was 8 minutes ago. When we observe Andromeda, we are seeing light that started its journey 2.5 million years ago. Powerful instruments allow us to see quasars, which are incredibly bright centers of galaxies powered by supermassive black holes. The light from the most distant quasars we observe has been traveling for billions of years. This allows us to look back to when the universe was very young, just a few 100 million years old. This is how astronomy works. It is literally studying the past through light. The speed limit also defines what is possible for travel and communication. If we wanted to reach the nearest star system, Alpha Centauri, which is 4.37 light-years away, the journey would take monumentally long. Even tiny robotic spacecraft pushed by enormous lasers, a highly speculative technology, might take over 20 years to reach that star system. Even after the arrival, the fastest possible communication back to Earth would take over 4 years. The cosmic distances combined with the speed limit make interstellar travel an enduring challenge. The speed of light, c, is not just a maximum speed, it is a fundamental constant that defines the limits of reality. This single rule shapes space-time, dictates how matter behaves when accelerated, and gives us the ability to look back at the origins of the cosmos. The existence of a fixed speed limit for light confirms that the universe follows strict, elegant rules. This limit is the direct result of energy and mass being equivalent, forcing anything made of matter to demand impossible amounts of energy to accelerate to c. Only massless energy like light and gravitational waves can travel at this constant velocity. The theories that explain this, introduced by Einstein, are complex, yet they have been overwhelmingly supported by observations, from the bending of starlight around massive galaxies to the discovery of gravitational waves. If you want to understand space, Like a NASA-level analyst quick without studying for years or paying thousands for a university degree, we have a free community that will help you. Link is below. We continue to test these boundaries, looking for deviations that might point toward a deeper, unified theory that could explain what happens in extreme environments like the singularity of a black hole. The speed of light forces us to accept that the universe operates in slow motion across vast distances, but in doing so, it preserves the history of the cosmos for us to observe. The entire story of cosmic evolution is laid out before us, delayed only by the finite speed of its messenger. If you want to explore the sheer scale of the cosmos defined by this speed limit and understand how much of it is truly empty, click here to the universe's almost empty video.